So last time we have talked about covering number. So covering number is the upper bound for the Rademacher complexity. And then our goal is to bound covering numbers because this is a new tool for bounding the Rademacher complexity. And we have discussed what are the bounds for linear models. I didn't show any of the proofs, but there are some existing bounds which are 20 years old, actually. And we also talk about the Lipschitz composition lemma for covering numbers, which is much easier than the corresponding lemma for Rademacher complexity. So basically, if you know a function class has good covering number bounds, and then you compose it with a Lipschitz function, then you still have a reasonable covering number bounds. So that's the general idea. And then today we're going to talk about deep neural networks. And we are going to use some of these tools because you can see that a deep net is actually composed of multiple linear models with some of the Lipschitz functions, right? The activations. So this is the goal of this lecture. So let me set up the. Actually, sorry. Give me one moment. I think I probably have to change the mask because I'm always having the fog. I don't know what happens with this mask. Let's change one. Maybe there's some deficiency with the mask. Sorry. Okay, let's continue. So we have a neural network. So the setup is that we have some neural network that's called H theta. Theta is used to denote a set of parameters, and we have R layers. So the network looks like this. So the last layer we don't have any activation, and then you have some activation, and the next layer you get R-1, something like this. So basically, if you do the ordering of the math formula, so you first multiply x with W1, and then you pass through a nonlinearity, and then you multiply W2, and you do this so on and so forth until you have R layers. This is the network. So there are R layers, and Wi are the weights. And the kind of the bound that we're going to talk about is that so here is the theorem. So assume xi2 norm is less than c, and consider a family of networks is a H theta with some norm control of the weights. So we control the operator norm of the weights to be kappa I, and we control the 2-to-1 norm of Wi transpose to be Bi. And then suppose you control your complex function class like this, then the Rademacher complexity will be less than up to constant factor C over square root n times the product of kappa I times the sum of, this is a complex formula, let me explain it in a moment. I from 1 to R, 3 over 2. So, or alternatively, as a corollary, I guess this is not necessarily that formal because you have to talk about, what exactly this is. You have to have some failure probabilities. But, roughly speaking, you are saying that generalization error is less than O tilde 1 over the margin times 1 over square root n times this times C times the product of the operator norm times the quantity. I guess here I'm using the right, so times the norm. A little bit. Okay. Anyway, so basically the important thing here is that the complexity measure depends on a few things. One thing is that the operator norm of the weight matrix, and it depends on the operator norm as a product. So the complexity in the complexity term, it shows the product of the operator norm of all the weights shows up in the complexity. And also there's this term, which basically you can think of this as a polynomial in kappa I and bi. So this, you can in some sense think of this as a polynomial of kappa I and bi, which is not really important, right? So as long as it's polynomial for us, it's not that important, because the product of the operator norm probably will be the dominating term, and that the polynomial in bi and the kappa I probably are somewhat kind of like, anyway, relatively small. So we don't necessarily have to care about exactly what this 2/3 means. Actually, they don't have any special meaning. It's really just something that comes out of the proof. But as long as they are polynomials, we are relatively happy with it. And so basically, this is the important term. And this term, if you look at the bound, it comes from the Lipschitzness of the model. So kappa I is the bound on the Lipschitzness of a single layer, and the product of kappa I is the bound on the Lipschitzness of the product of all layers. So so without any details, I think this term, you can imagine this comes from some Lipschitz compensation, some use of Lipschitz compensation lemma.
What is the thing right above the x in the expression norm of x is less than or equal to c?
This is assumption? Sorry.
There's like a symbol that you wrote right above the x.
This is I? Yeah. Oh, you assume that it's true for every I. I think this can be relaxed a little bit, but again, it's not very important. So you can maybe relax it to be the average of xi is less than c. It's not super important.
Can I ask you, what is the operator norm?
Oh, right. So that's sorry. So the operator norm is the, I guess maybe I didn't. So this is also the spectral norm. Also the largest, the single. So this is the spectral norm. Oh, the largest singular value. If any of this makes sense to you, and and also the formal definition is just that the max over x. So I guess I call it operator norm just because this is if you think about W as operator, then this is saying that how does this operator change your norm, right? So if you give it a 2-norm vector, then how does it change the norm? Yeah. So okay, cool. So and you can kind of see that this is kind of like about the Lipschitzness. This is also, maybe I should expand this a little bit. So this is also about the Lipschitzness of the linear model Wx, right? Because if you care about the Lipschitzness, what you have to verify, that Wx minus Wy is less than some constant times x minus y. And what that constant should be, right? So if you prove an inequality, then you're going to get the operator norm or spectral norm of W there. So that's why this is corresponds to the Lipschitzness of a linear model. Any other questions? Okay, cool. So, by the way, I haven't got any questions from Zoom for a long time, so you should feel free to ask questions. Just you don't have to, but of course, feel free to unmute yourself. And okay, so how do we prove this? So the fundamental idea, so in the next 30 minutes, we're going to talk about this proof. The fundamental idea is that you somewhat kind of cover your function set iteratively. So cover this set of functions f iteratively And iteratively means that you cover more and more layers gradually. And how do you do this iteratively? You have to use the Lipschitzness, in some sense, the Lipschitz composition lemma that we have discussed. And also you want to also control, and also controlling how the error propagates. Right. So that's a high-level summary. It's kind of abstract, but let me dive into the details. So for simplicity, let's try to abstractify each layer of f. F as fi. So basically, fi corresponds to a linear multiplication, a matrix multiplication plus an activation layer. Right, so this is a one layer, and then you can write f. Then you can consider f as this composition of fr with fr minus 1, so on and so forth. Right. So basically, for every layer, you have certain choices. You can choose your weight matrix, and then you compose all of this function class. By this composition, I guess we have used this notation multiple times. This is really just means that you're looking at fr composed with fr minus 1, composed with f1, where each fi is from the family of capital Fi. Okay, so this abstraction will allow us to kind of have much cleaner notations. But fundamentally, you should just think of each of the FIs as a layer, right? So and what we know is that so suppose maybe let's say, so for the sake of kind of like preparation, so suppose for every f in fi in little fi in capital fi is kappa I Lipschitz. This is actually the case for us because we restricted the spectral norm of, or the operator norm of each of the wi's to be less than kappa I. That means that every layer is kappa I Lipschitz, right? So and the value is 1 Lipschitz. So even you compose with activation, it's still kappa I Lipschitz. So suppose each of these functions is kappa I Lipschitz, then you know that fix. So these are just some preparations. So 2 norm is less than kappa I x minus y 2 norm, and maybe let's just for simplicity suppose fi 0 is equals to 0. This is also the case in the real case we care about, where you have like a neural network. So and also let's suppose that xi is less than c. This is also our assumption. So then with all of this, then you know that we know a bunch of like basic things. So for example, we know that you can bound what's this? What's the multilayer application of on xi? What's the norm on the bound on the norm here? So the bound on the norm can be bounded by each time you may at most capture a kappa I factor. So you get kappa I times kappa I minus 1 times kappa I minus 2, so on and so forth, times kappa 1 times c. Right. So and we call this ci. And let's define this to be equals to ci. So basically, this is some basic kind of like a preparation. So under this abstraction, you know some bound on each of the layer, and you know each of the layer is Lipschitz. And what we're going to do is that we're going to do two things. So for 2 steps. So first, you control the covering number of each layer. And second, you have a combination lemma. You compose this, like combine them together, like a. So like you have a lemma that turns the each layer, right? So you turn each of the layers. So you have a lemma that turns single layer covering number bound to multiple layer. Layers. So, and I think number one is kind of easy because for number one, this is just a linear model composed with a Lipschitz activation, right? With one Lipschitz activation, you can just invoke what we have discussed last time, right? So basically, the important thing is that how do you turn a single layer covering number bound into multiple layer covering number bound? That's basically the main thing I'm going to discuss. So let's call this. There's a lemma that does this. So under the assumption setup above, and the kind of like the relatively abstract setup above. So suppose you assume for every n inputs, with L2 norm less than CM minus 1. So these inputs are used to define Pn, right? The L and Lpn, and the metric L2Pn. So this is the inputs for which you are evaluating your covering number, right? So if you to define covering number, you have to define the metric, define which empirical inputs you are evaluating on, right? So I'm assuming that for every input of this norm constraint, you have a covering number. You have a covering number bound. So you know that epsilon I fi L2Pn is less than some function of this and CM-1. Some function of the norm and some function of the target radius. So this is just assumption. This is assuming that, so basically this is assuming that you have a single layer bound. Single layer bound. So suppose you have a single layer covering number bound of this form, and you do have this bound. It's just I didn't give you the exact formula, right? So if you instantiate on a linear model, you are going to get something like this. This will be something like Cm minus 1 square over epsilon square, right? The norm of the input square over epsilon square, right? So that would be what happens when you have linear models. But suppose you have the single layer covering number bound, then the conclusion is that you can turn this into a multi-layer covering number bound. And the form of this translation is not very clean, but it's like this. So there exists an epsilon cover of Fr composed up to F1 for epsilon is equals to the following thing. Sorry. One more. Let me finish. Okay.
What's the symbol on the right is the function epsilon I and Cm as well.
Sorry, can you say it again?
In that expression, if log n is less than something.
Sure.
What's that symbol?
This is G.
G.
Yeah. So I'm assuming a generic thing here. But actually you can just for the abstraction, like when you really use it for linear models, it's going to be something like CM-1 square over epsilon I square. So right. So this is G. And then so there exists an epsilon cover such that with this size, such that the log size is bounded by the log size of this cover is bounded by sum of G of epsilon I CA minus 1, and I from 1 to R. So basically, if you have a log covering number bound of this form for every layer, then you can have a log covering number bound for this thing, and the bound just the log covering number just add up in a sum. But the tricky thing is that it's now like the cover size also grows. So the cover size also kind of add up in some way, which is a little bit kind of like complicated. So basically, your cover size is kind of like multiply, it's kind of added in some way where you also multiply some of this kind of like kappas, which are Lipschitzness in some sense, and your covering number is also added in some way. So this is the fundamental mechanism for us to turn a single layer bound to multiple layer bound. Of course, I'm going to use this in some way at the end so that we get a final result, because you have to choose what epsilon i's are, right? So eventually what you do is that you're going to choose epsilon i's so that you get the desired target radius, and you work out what exactly this formula should be for that particular choice of epsilon i's. Does that make sense so far? Right. So, but before doing that, I'm going to first prove this lemma, and then I'm going to do the derivations, right? So after you have this is the core, right? After that, this is just a choose parameters. You just choose epsilon i's in some way that is in favor of you, and work out what is the final bound. Okay. So, and in some sense, the interpretation of this lemma is that you can add up the covering number bound, the log covering number bound in this way, as long as you pay some additional radius. Like, okay, so this proof is in some sense, in some sense, it's actually pretty simple, but the exposition, requires some challenge. Like it's a little bit challenging. So the fundamental idea is the following. So we start with this data point. We start with this concatenation of n data points, right? So you have n data points, and you map these n data points to a set of points, right? This is the Q that we talk about. I think I need to draw this in a good way so that I have more space. So let's start with, you start with n points, and you map these n points into a vector of dimension n, or maybe actually it's a matrix of dimension n. So you map this to some space, and each of these points here is the concatenation of fx1 up to fxn. And this is the so-called Q, the set of Q, right, that we have to cover, right? So, and you can use multiple functions f, right? You can use any function f1 in f1, right, to map to a different point. If you choose different f1s, you're going to map to different point. And if you just have one layer, what you're going to do is that you're going to cover this set Q, right? That's what we do for covering number for one function, for one family of functions f1, right? So, right. So then what you do is that I'm just basically reviewing what we have done for covering numbers for one family of functions. You create this kind of like bowels, right? So that covers it. So basically you create like these centers, and these are points that are in C, right? Maybe let's call it C1. So let's create, let's say C1 is epsilon 1 cover of F1, right? This is what it means, right? So, and now we are going to see how do we turn this into a cover for F1 composed with F2. So that's kind of the job we are trying to do. And what's really going on here is that, for every point here in the output space of, right? So this is maybe let's call this Q1, which is the output space of, maybe let's call this thing capital X. So then Q1 is the family of outputs, where the function has to be chosen from F1, right? So, and what's the composed? So how about, if you have F2, another layer? So what happens is that for every point in Q1, you can apply multiple different functions, right? For any functions, little f2 in capital F2, you can apply it to map to a new point in the new space, right? To map it to a new point. So you get for every point here, you get a bunch of possible outputs, and for every point here, you get another bunch of possible outputs, right? So each of these new points could be your image after applying 2 layers, right? So now we are trying to apply. We're trying to cover this new set of outputs, like Q2, let's say, and how do we cover it? So the approach that we are going to take is somewhat kind of like in some sense, pretty brute force. What you do is you say you want to leverage the existing cover for capital F1 in some way. So what you do is you say you look at a center here in C1, and you look at what are the image of this point after applying a second layer. So you get something like this, right? So this is the set of the image or the output of this point. So maybe let's say, suppose this point is called F1x, which is in C1. Let's call this F1 prime x, which is in C1. And then you look at all the outputs from F1 prime x. So you get this family of points where you apply F2 on F1 prime x, and where F2 can be chosen arbitrarily from F2. Okay, so, and now what we do is that we cover this set by a new epsilon cover. So what you do is you say, I'm going to cover this with a bunch of things. And what does that mean? That really means that you choose a subset of capital F2 and cover, because here you are arranging over all possible functions in F2, right? So if you want to choose a cover for it, you just say, I'm going to drop some of them. I choose a subset, a discretization of capital F2. So that's basically the approach. So, and you do this, and then you do this for every possible points in C1 and cover them. So basically, suppose you have another point in C1 here, and then you look at all of its image, and then you do another set of cover. And you do this for every possible point in C1, and every possible point in C1 have induced a set, and that set can induce a cover, and then you take the union of all of these right balls into and that the union of all of these right balls becomes a cover for the Q2. Right? For example, suppose you have, let's say, F1 prime x here, right? Then maybe I should use a consistent color. Let's say you have F1 prime x, and this is mapped to this set of points. Here, this is the set of all F2 F1 prime x, where F2 is in capital F2, and then you create a cover for this set so that you can discretize F2 again. And then you take the union of all of this right cover, of this right balls as your cover for Q2. So any questions so far? So formally, what we should do is the following. So so epsilon 1 and epsilon r are the radius on each layer. These are just which are TBD. You choose these, I guess in this lemma, they are not TBD. They are just already given to you. Eventually, you'll choose something, choose some numbers for them. And then what you do is that C1 is the epsilon cover, epsilon 1 cover of F1. That's easy. And then you say that for every F1 prime in C1, construct this C2, a cover in the second space, but this cover depends on F1 prime. So to epsilon 2 cover the set F2 composed with F1 prime, which is defined, which is what I wrote above, right? This is F2, F1 capital X. F2 is ranging in capital F2, right? So for every set like this, right? This set is really literally these blue things I drew here, like this blue set, and I choose a cover, and I denote that cover to be C2, comma F1 prime, because this cover depends on F1 prime. And then I'm going to take the union. So I'm going to let C2 to be the union of all of these C2 F1 prime, where F1 prime is in C1. So this is how do I construct the cover for the second layer. So this is supposed to be a cover, supposed to be a cover for capital F2 composed with capital F1. Okay, any questions so far? So there are several questions, right? So one question is that, how good this cover is, right? That's one thing. And the other thing is that how large this cover is. So the size of this cover is relatively easy to compute because you are basically just blowing up the size multiplicatively. Because for every one in the C1, you create this cover, right? So you just multiply basically the covering numbers together in some sense. And that's easy because you can formulate what you can do is that you can say C2 F1 prime. This is something, the log of this is going to be bounded by G of epsilon 1 C2. Epsilon 2 C2. But this is epsilon 2, my bad. This is epsilon 2 C1, I think, in my notation. So epsilon 2 C1, below C1. This is my assumption because my assumption is that as long as your input is bounded by C1 and your cover size is epsilon 2, you have this bound, right? So and also, so that means that the size of C2 is bounded by the size of C1 times this exponential of this G of epsilon 2 C1. Because for every point in C1, you have a bound for that corresponding set. So then you just multiply by C1. And that means the log of C2 is less than the log of C1 plus G of epsilon 2 C1, which is equals to G of epsilon 1 C0 plus G of epsilon 2 C1. I guess actually I forgot to define C0. C0, just for convenience, let's define, my bad. So define C0 to be just the C, the bound on the input. So CIs are the bounds on the layers, the activation layers. And C0 is the bound on the inputs. Right, so, okay. So, so basically the size is added up. The log size is added up. That's easy. And we're going to deal with the covering. How does the covering works, like at the end. So before doing the covering, computing the covering radius, let's define how do you proceed with more layers. So similarly, for given CK, suppose you have covered K layers, then now you are constructing a cover for the K plus 1 layer. So what do? You say that, so for any Fk prime composed with Fk minus 1 prime, F1 prime in CK, you construct some ck plus 1, which is a function of this fk up to f1 prime. So that epsilon k plus 1 covers the set fk plus 1 composed with fk prime. So and you like this ck, the final cover, to be the union of all of these kind of sets. And similarly, you can prove that the log of the ck plus 1 will be less than the sum of all the single layer covers, epsilon k plus 1, ck plus up to g of epsilon 1, c0. All right, so I've shown you how to cover it. It's just an iterative cover that's kind of pretty brute force in some sense. And now the question is why this is a good cover, right? What's the radius? So basically, we need to answer the question, right? So for every fr composed up to f1, which belongs to this fr, this set, right? This is the set we want to cover. So you pick a function in this set, and you want to say that this can be represented by something in the cover, right? With some small distances. So how does that work? So you first say that you know there exists S1 prime in C1 such that rho of F1 F prime, this is less than epsilon 1. That's something you know, because C1 is a cover, epsilon 1 cover of the capital F1. So now you have to say, let's say you try to pick something in C2 that can cover F2 composed with F1. How do you do that? You basically, in some sense, use the construction. You say that maybe I should draw this a little bit more. So, okay, so the first thing is suppose you have a function here, or you have a point here, which is f1 of x, right? So you cover it by this point. Oops, how do I do this? As you cover this by this point, right? So now, suppose you have a point in the second layer. Suppose you have a point somewhere here, which is the map, which is computed from that f1x, right? You apply some f2 to it. So, and what you do is you say that you first look at the neighbors in the first layer. So you got this point. And this point, you look at what's the neighboring, what's the image of this point in the second layer, maybe something here. So I guess here you're applying, I guess let's assume you're applying f2 here. So you get f2 here. You use the same f2 on the cover, and you get this point. And then after you get this point, you look at the neighbors in the right. So you got this one. So basically, this will be the cover for the purple point. I'm not sure whether this makes sense. Sounds good? Okay, so in other words, in more formally, so basically you say that, so you want to say there exists a function in this cover, right? In this C2 F1 prime. So this is this one is at the right point, I think. This is that right point. So it's in this cover such that F2 rho of F2 F1 prime is close to what? It's close to this the blue point. What's the blue point? The blue point is F2 composed with F1 prime. You know, this is less than epsilon 2. Right. So yeah, I guess maybe let's write this as f2 prime composed with f1 prime, so that just to make it looks kind of like a, you know, that's also what my cover is doing, right? So suppose 0 of f2 prime composed with f1 prime. So your cover has this structure that you will first apply f1 prime and then you use the f2 prime in the cover, right? So suppose, sorry, what I'm saying here? Okay, sorry, my bad. So you have this function in this cover such that so this is of the form, let's say f2. I don't want to make this too complicated, but I think let's say this is of the form f2 prime composed with f1 prime, which is in this cover. But this one actually implicitly depends on f1 prime as well. But let's ignore that notation. So you get rho of f2 prime composed with f1 prime, which is close to f2 composed with f1. But this point is not what you really want to cover, because you want to cover f2 composed with f1. So what you care about is that rho of f2 prime composed with f prime, the difference between this and f2 composed with f1. So this is the thing you really care about. And you can see that there's still some differences, because the differences come from that this is f1 prime, but not f1. So that's why you do a triangle inequality. You say that the target is less than rho of f2 prime composed with f1 prime. So you use this as the intermediate term. Right, so this one is less than epsilon 2. And you are left with this thing that where you only differ in the first layer, right? That's the difference but this difference is kind of like propagated. In some sense, if you look at this figure is a little bit kind of like tricky. So this is the difference in the first layer. But once you apply this F2, right, so you have a bigger difference. So this is the difference in the second layer. And this difference can be kind of like blow up a little bit, because even though you apply the same function, you may blow up the differences a little bit. So that's why you have to use the Lipschitzness to say that this is less than epsilon 2 plus kappa 2 times epsilon 1. Or maybe kappa 2 times rho of f1 prime, f1, and this is the less than epsilon 2 plus kappa 2 times epsilon 1. That's how you bound the covering, the radius for the second layer. Any questions? And then you can similarly do all of this, in the for k, which there exists a function fk prime, which depends on f1 prime up to fk minus 1 prime, and in this set ck, let's write this as fk prime composed with fk minus 1 prime composed with f1 prime, and such that this is a cover such that the distance is less than epsilon k, less than epsilon k. That's the definition of the cover. And then you have to kind of like see why this is a good thing for the original one, right? You call that this is not actually what you really care about. You care about the fk composed with fk minus 1 up to f1. You don't care about the prime. So you care about this. This is the thing that you really care about. You want to show this is small. And how to do this? You kind of expand this into multiple terms. So you say that this is less than so I guess you the first thing is you first compare with this kind of telescoping sum is pretty actually useful in many cases. You first compare with this, and then you compare. You just gradually pee off, more and more terms. This is no prime here. And then until finally you got everything is kind of no prime basically. And eventually you get what you care. There's no prime at all. So this is just triangle inequality. And now you bound each of these terms. The first term by definition is less than epsilon k. And the second term, you see that these two are the same. And this part is also the same. And the only differences come from the difference between this fk minus 1 and fk. The f prime k and f prime k minus 1 and fk minus 1. So because of the cover, that give you epsilon k minus 1. And then you also have to blow up a little bit because of the fk composed on top of it. So you also have to pay a Lipschitzness of fk, which is kappa k. Kappa k. Sorry, my k and kappa looks probably almost the same. And then you have epsilon k minus 2 times kappa k minus 1 times kappa k, so on and so forth, until you have, in the last time, the only difference come from the first one. So you pay epsilon 1 because they are epsilon cover. F1 prime is from the epsilon cover. And then you pay a lot of Lipschitzness, like kappa k times kappa k minus 1 up to kappa 2. So and if you take k to be r, then you get the eventual thing, right? So the eventual theorem is that your radius for the final covering is something like, where is it? Oops. So the radius for the final covering is something like this, right? So that's eventually what you got. Any questions?
I'm still a little unsatisfied with having to add epsilon to the triangle inequality that we set. I guess if I'm picturing it, we have set points, which are examples, we can map into some larger set just with C1, or which is covered by C1. And then we're mapping the centers of each of those to the sets that we then cover. I guess I'm like, why isn't it like epsilon 1 times I guess it'd be kappa 2, kappa 3, kappa 4, or up to kappa k if I want high cover.
Right. So I guess the question is that why you only have to, why don't you only require this? This is because, like, suppose let me try whether this works. Suppose your function class is like f1 composed with a fixed function. Maybe it's the other side. So f1 composed with a fixed function, let's call it f2 maybe, composed with f3, so on and so forth, fr. And all of these are fixed. Then you only have this term. But this, you also have to cover the possibilities for the second layer, the third layer, so on and so forth. So that's why you have to pay the other term. Okay, cool. So now we are done with this lemma. And now let's go back to the proof of the theorem. And the proof of the theorem, as I kind of alluded before, is pretty much just the kind of annoying calculation in some sense. there's a way to do the calculation in a simpler way, but I'm going to first show you a zero knowledge proof. So basically, I'm just going to tell you that I'm going to choose my epsilon I to be this, and it just works out. And then I'm going to show you some way to kind of like at least what I would do with this. If I write a paper, I'm going to show you the first proof I'm going to show, which is just choosing some epsilon I. So if let's start with that. So basically, everything is about choosing epsilon I, right? So you first, okay, of course, you first know that this for is equals to O tilde of Cm minus 1 square bi square over epsilon I square, because this is linear model. This is linear model composed with one Lipschitz function, right? So recall that each of the Fi is a linear model composed with the one Lipschitz function, a fixed one Lipschitz function, and for the linear model, the covering number, the log covering number, is supposed to be something like the norm of the input, and this is the Bi is the Wi transpose 2 to 1 norm, right? So the norm of the parameter, and divided by the radius. This is what we have shown last time. Like we didn't prove this, but this is the lemma we had last time about the log covering number of the linear models, right? So we plug in this, and then basically, so basically you have two quantities, right? So one is the log covering size, which is the sum of Cm minus 1 square bi square over epsilon I square. And also you have another thing which is a radius, which is sum of epsilon I. I'm writing it as a sum kappa I plus 1 up to kappa r, right, from 1 to r. Right, so you basically have these two things that you want to trade off. You want to find the best dependencies between them. You want to make the log covering size to depend on the radius as best as possible. So you just choose some epsilon I, and so you care about the best kind of trade-off all the dependencies. So this is epsilon. So what you should do is that you should say, I guess, if I give you a zero knowledge proof, I'm going to choose epsilon I to be Cm minus 1 square bi square over kappa I plus 1 up to kappa r, a third times epsilon sum of bi 2/3 over kappa I 2/3 product of kappa I 2/3. Right. So if I choose epsilon I to be this, then I will claim that sum of epsilon I kappa I plus 1 up to kappa r, this will be indeed equals to epsilon. And why is that? I'm going to do this tedious derivation for you, but I don't feel like you should really need to verify it on the fly, or you don't necessarily have to verify it later. But just for the sake of completeness, let me do the calculation. This will be, this is, you just plug in epsilon I here, so you get, I think Cm minus 1 2/3, bi 2/3. This comes from these two terms. And then there's some thing about this and this. And also this thing, right? So you can organize those things into, I guess I'm treating this as a constant for the moment in this derivation. So I get this multiplied with this, we get 2/3, kappa I 2/3. Anyway, if you don't want to verify this, just maybe bear with me for a second. All right, so epsilon. And then I guess one thing is that Ci is also a function of kappa I, because we recall that Ci is the norm bound for the layers, which depends on kappa I. Question?
Yeah, so the I of the sum and the product rule, that's different from the epsilon. The I and epsilon are actually
the I here? This is the same I. Oh, sorry. Oh, you probably, yes, you're right. You probably should use a different index just for the sake of, yes. So if you want to, I think you might write this. It's probably okay, right? You know what I mean. But ideally, you probably need to use a J just for the sake of completeness. So yeah, but this one you average out this part, like the after doing the sum and the product, the I is gone in the second part. So anyway, so let me do this tedious thing. So recall that Ci is the norm bound for, so and Ci is defined to be, I think Ci is defined to be some product of kappa i's. And so we got, I guess let's put Bi in the front, and then you get Ci is kappa 1 2/3 up to kappa I minus 1 2/3. This corresponds to Ci minus 1. And then you get kappa I plus 1 2/3. That's from here. Wait, this is kappa plus 1, I plus 1, sorry. And then you still multiply the same thing here. This is, and then you simplify this to the first sum to, I guess you can see that the only missing term is kappa I. So this is equals to Bi 2/3 over kappa I 2/3 times product of kappa I 2/3, I from 1 to R, and times this thing. And now let's deal with this thing. You can see that this one cancels with this one, cancels with this one, and this one cancels with this one. So you get really equals to epsilon. And the log covering size is equals to what is equals to the sum of the what I'm doing here is equals to this, basically the sum of, okay, let's first write the trivial thing. This is Ci minus 1 squared Bi squared over epsilon I squared, and you plug in epsilon I here, so you get this gigantic thing. Maybe let's call this thing Z. So you get 1 over Z squared times this one's sums of Ci minus 1 squared Bi squared. You plug in this to the minus 2, so you get Ci minus 1 squared Bi minus 1 squared minus 2/3, and then kappa I plus 1 up to kappa I 2/3, and there's some cancellation. So this will be equals to, I think, sum of wait, sorry, I think this, wait, I think I jump a step in my notes, so I need to so sorry. I think you plug in the definition of Ci-1, then you get Bi 2/3 over kappa I 2/3 times the product of kappa I 2/3. And now you use the definition of Z, which is this gigantic constant. And eventually, I think you get, let me not do that carefully, but eventually you get this. Over epsilon square. Okay, so I guess maybe this is a good demonstration of why I shouldn't do this, right? Like even after I verify this with my notes, which has almost all the steps, is kind of tricky. But anyway, so before talking about how to do this better, I guess let's first agree that this is done, right? Because now you see the log covering size is bounded by this epsilon square, something over epsilon square, and that's what we wanted to have. And then you apply the Rademacher complexity. Apply the Rademacher complexity, the tool from covering number to Rademacher complexity. Recall that if you have log covering number, is R to R over epsilon square, then this means Rademacher complexity is something like square root R over N, right? So this is what we discussed last time. And if you apply this small tool, then you get the Rademacher complexity will be this one, square root of this one and over square root N, and then you are done. Okay, so we are done, but I think I want to kind of share how to do this a little more easily without going through all of this pain. This is a small trick. It's purely a mathematical trick. I don't know how many of you know it. Maybe you all know it, or maybe you all don't know it. But anyway, let's talk about it. So basically, the question is, you care about, right? This is the question. You care about the trade-off between these two. So, and you care about the trade-off between these two. And so what you could do is that if you abstractify this, it's kind of like, so abstractly speaking, this is about the trade-off between something like AI, maybe let's use some different numbers, say alpha I square over epsilon I square versus sum of beta I epsilon I, something like this. Right, that's kind of the game you are dealing with. And how do you do the trade-off? I think, so what you would do is that you can use this so-called Hodel inequality. So the Hodel inequality is that there are multiple ways to write it. For example, you can write A in a product with B is less than the P norm of A times the Q norm of B when P and Q satisfies this. Right. So and for example, when P and or you can also write it like this: the sum of AI BI is less than sum of AI to the power P to the 1, this, something like this. Right. This is just exactly the same thing. And I guess when P is 2, this is the Cauchy-Schwarz inequality. And we need something slightly different. We need P is 3, where Q is 3 over 2. Then you got sum of AI cube, a third times sum of BI 2/3 is larger than sum of AI BI. So in some sense, all of this inequality is trying to kind of deal with, has this kind of form. And I guess maybe which one should I do first? Like, I'm not sure whether I'm lost in you. So like, I guess what eventually I want to do is the following. Maybe let me just give you an overview. Eventually I want to do is just that I want to do this. I want to say that this product with the sum of beta I epsilon I, this is larger than sum of alpha I beta I to the 2/3 and 3/2. So if you're able to do this, then you kind of like cancel out. So maybe let me do this first. So we care about sum of alpha I squared of epsilon I squared versus sum of beta I epsilon I. And this is your epsilon, and this is your covering size, the covering. And what you can do is that you can say this times this square. Just forget about this. Just let me do it formally. So there's an inequality that shows that this is larger than sum of alpha I beta I to the 2/3 over 3/2. And this is essentially Hodel inequality. Let me justify this in a moment. But suppose you believe in me in this, then you say that, and suppose you also believe that this is achievable. Suppose you believe that equality is achievable, which I will justify in a moment. So if equality is achievable, it means that there exist epsilon i's such that sum of alpha I square of epsilon square is equals to this quantity 3/2 over sum of beta I epsilon I square. And recall that this is your epsilon square, and this is your log covering number. Then you get log covering number. You can so you get that you can choose epsilon I such that the log covering number is less than this, which is equals to this quantity over epsilon square. And this quantity is what you are looking for, right? This is the R thing that you are looking for, which is something like this. And you don't have to do any of this verification, right? That's it. And basically, you just have to plug in alpha and beta I, and you just verify, and that's it. So does that make sense? So basically, you cancel out the epsilon i's. You try to find the best epsilon I by proving the best inequality you want, and you also want the inequality to be achievable. So for example, another situation that this is useful is that, for example, you probably have seen this kind of bond. Like you have a parameter eta, you have the eta plus b over eta. You bound something like this, and you can choose your eta arbitrarily. So how do you do it? Many people tell you that you just find out the minimum eta by doing some kind of like taking a gradient, right? So and you find out the minimum eta, right? That's fine. But my way to do it is that I just prove that eta plus beta eta, this is larger than 2 times square b. This is Cauchy-Schwarz or like AMGM, whatever you call it. And this inequality is achievable, right? You can attain the equality so that basically the best thing for this is 2 square b. Basically, if you know this is inequality is attainable, then you know that you can choose there exists the eta such that eta plus b over eta is 2 square b, and then you get rid of the eta. You get the best bound you want. So the same thing, it's the same logic here as well, right? You prove an inequality so that you can cancel out the parameter that you want to choose, and then and if that inequality can be attained as an equality, then you know that you are getting the best parameter, and you don't even necessarily have to compute what epsilon I are. Of course, when you write a paper, probably you still want to compute epsilon I and do the zero knowledge proof, right? That's why all the papers show you these kind of things, right? So because so how do I have to do a lot more argument, right, to show that this. But in your mind, you probably should do this later version. This later version, at least this is what I did in my mind when I do any research like this, right? Because this is so fast, so that you can get an estimate on what's the bound you can have, right? So, and in some sense, this is useful. In many cases, because one of the way to make your theoretical research faster is that you have a lot of modularized small steps, which you can do very, very fast, right? So one of the way I found that people can get into this very messy calculation is that this, every theory, if you prove something hard, right? So you have to use a lot of pages, right? So you like your eventual product is something like 20 pages proof, or maybe more than that. Sometimes there are 70 pages proofs, or like 100 pages, right? So at least I think at least when I do those kind of like proofs, I never really kind of like, if I change one part of it, I never have to redo that 100 pages calculation to know what's the final outcome. So basically, after a certain point, I already know that this part, maybe these 2 pages are the most important thing, and I also know that how does this page translate to the final outcome. And I've already done those kind of like very fast. I have a kind of like a very fast data structure, so that I know that if these two, if this part can be improved by a factor of 2, then what does that mean for my final outcome? And that part is kind of like already abstract enough so that you have this very fast conversion, and then you can iterate very fast. So it's the flip side is this is opposed to another model, which is that you change your proof in some part, you have to redo all the other parts, and so that would be much slower. So this is one of this kind of tricks that I realized that so if you can do something small like this kind of abstract things very fast, then you can iterate faster in your research. Anyway, so far it makes sense. And if you really care about why this inequality is true, I think I was trying to justify why it's true, because you can just use Haldane inequality. I guess if you apply the Haldane inequality, you get something like this. And this is still not exactly like this, I think. So, oh, actually, this is exactly like this, right? Because you have to choose, you can choose your AI to be, you just say AI cube maps to this, and BI maps to this. If you just want to verify, right? You just have to change it, right? So, but again, if you have to verify this, by matching it, it's still too slow to me. So what I do is that I also memorize other different versions of this Haldane inequality so that I can do it faster. I think the version I memorize in my mind is that at least one version of the Haldane inequality in my mind that I memorize is this, which is something like sum of UI square times 1/3 times the sum of VI 2/3 is larger than sum of UI VI 2/3. Something like this, which is even closer to here, right? Because in some sense, the way you to memorize is that if you have a bigger exponent here too, then this 2 will go to the VI. How do I say this? So basically, you put the so why this is UI to the power 2/3, right? So why this is UI to the 2/3? This is because here you have a square, and then you have a 1/3 outside. And the reason why here you have VI to the power 2/3 is because inside you have VI, the linear term, and then outside you have the 2/3. So if you know that, then you know that if you have a square here, then you can cancel this epsilon I, because epsilon I will be squared, and here you have epsilon I squared, so they can cancel each other. I'm not sure why this makes any sense. Like it takes some practice. If you see this enough times, you know what kind of inequalities you can prove. Anyway, I guess I probably should wrap up this discussion. Any questions? Okay, I think, let's see, 10 minutes. Okay, so I guess I'll use the next 10 minutes to motivate what I'm going to discuss next. Go ahead. This inequality? Because the equality can be achieved, so that's why it's the best choice. Oh, you mean the final bound? Okay, yeah, maybe let me discuss that. I'll answer that in the next 10 minutes. Yeah. Right, okay, so basically now next we're going to do something more better than this. So and actually it turns out the proof is actually cleaner to some extent, because it's in some sense because it's capturing the right quantity. So next we're going to have generalization bounds that depend on the actual Lipschitzness. And I'm going to argue that the Lipschitzness we had before was only an upper bound, right? Before we have this, right? Before we have this, right? So before we have this bound where you have essentially a dominant term times other terms, which is just polynomial in the norm, which is not very important. And this one, this is only an upper bound on the Lipschitzness. Right, and it's a pretty worst case upper bound, because you have to, if you really want your network to be to achieve this Lipschitzness, you have to actually like kind of construct something that is kind of like somewhat kind of like special. And even this is achievable, right? This worst case upper bound can be achievable in certain cases. Still, you want to find out a network which is probably better than this empirically. So that's why we are going to kind of have replace. So basically, the high level goal is they want to replace this product of the spectral norm by something that is more accurate. And there are several motivations to do this. So I guess one thing is that, and this relates to the limitation of this bound. So one thing is that this Wi operator norm has to be larger than 1, or even you can arguably say this is even larger than square root 2 to make sure fx is not too small. Right? Why this is the case? This is because if you look at every layer, let's say hi is the ith layer. Define hi is the ith layer. Then hi plus 1, the true norm of it, is the true norm of this. You apply this last layer, and if you do a heuristic, you say that suppose you believe that this activation, this value activation, kills half of the coordinates. I say, right? So it zero out half of the coordinates. Suppose you have that kind of like, then it means that after value, your norm will reduce by 1 over square root 2, because you kill half of the coordinates. So of course, this is a very heuristic. This is just a belief, right? Like a assumption. And suppose this is the case, and then you say that this is less than or square root 2 times the operator norm of Wi times hi2 norm. So then you can see that each time you can only grow your norm of hi by this factor. So if Wi operator norm is less than square root 2, then you are shrinking your norm over layers. So your norm of every layer will become smaller and smaller, and eventually they will converge to 0. So your output will be very small. So that's why you have to make sure that the operator norm of Wi to be somewhat big. It cannot be like too small. In the most optimal case, I think you want the operator norm to be larger than 1. But in its kind of more typical case, you need it even to be larger than square root 2. So in any case, right? So this means that. So in some sense, this means that this the product will be big. So and another thing is that so motivation 2, I think this is something I mentioned, right? So this is only a worst case upper bound. It's very worst case of the Lipschitzness. And in practice, so the Lipschitzness on the data points, the Lipschitzness on the data point x1 and up to xn might be better. All the Lipschitzness on the population distribution, or maybe on the data points, or maybe on the x from P from the population distribution could be better. right? So and this bound doesn't capture that. And another thing is that it turns out that we'll discuss this, in the later lectures. So it turns out that SGD prefers flat local mean. This is something we widely believe, and in certain cases we can prove this. And the flat local mean is, roughly speaking, we'll show this, we'll justify this in the later lectures. But roughly speaking, this is like the Lipschitzness of the models on the empirical data. So you can see that this is not a Lipschitzness, the worst case Lipschitzness on all data points. It's the Lipschitzness on the empirical data, so which further justifies that probably want to have a bound that depends on the Lipschitzness on the empirical data, but not the Lipschitzness in the worst case. So and in some sense, and also another thing is that another remark is that it's okay to have a generalization bound that depends on the empirical data. So okay to make the generalization bound depend on empirical data on x1 up to xn, because and in some sense this is actually nice, because suppose a generalization is less than some function of the classifier and x1 up to xn. This is still useful because you can still use it as an explicit regularizer. So there's no problem that your generalization bound there's no problem for a generalization bound to depend on empirical data. You probably don't want a generalization bound to depend on the population data because you don't know how to regularize it anymore. But if it depends on empirical data, it's fine. So basically, concretely, in the next lecture, I guess we'll prove that. Next lecture, we'll prove that the generalization error, or the test error, the L of theta, is less than some function of the Lipschitzness of f theta on x1 up to xn, and then the norms of theta. And this function is a polynomial function which doesn't have anything exponential in it. Okay, I guess I'll stop here. Any questions? And interestingly, the proof for the next lecture is actually easier than today, I hope. I don't know how do you think about the proof today? Like, it's pretty brute force. So in that sense, it's actually not very hard, but it's pretty messy. Okay, I guess I will see you next week.